Okay, so in regards to standard deviation, we've got variability. Variability tells us how the data values differ from each other. And so a lot of times when we use variability, we would discuss range, because range tells us how much the variability is from the minimum to the maximum. But sometimes that doesn't tell the whole story. For example, I have these 3 data sets here, and they all have the same range. But what they don't give me is the idea that there's definitely something different going on in the center. In general, more variability gives you a larger range. But in this case, we have the same range, and we have 3 different sort of data sets. So I basically need a way to mathematically say that the values in this data set C are closer to the mean, and the values in data set A are farther away from the mean. Or in other words, I need something that's talking about the spread in the middle with respect to that mean value. So I might start off, and if I want to say, okay, well, if I want to know how a data set differs from the mean, I could literally check to see how it differs from the mean, like find the difference between each value and the average. So I could go here and say, I've got these 2 values, these 4 values, 1, 1, 4, and 4. The average value is 2.5. So if I took each of these, 1 minus 2.5, 1 minus 2.5, 4 minus 2.5, 4 minus 2.5, I could get the literal differences from the mean. And so if I wanted to know on average, how different are these values from the mean? Well, normally when we take an average, we add them up and we divide by how many there are. So if I go and I divide and see how many there are, and I get 0, which isn't very useful as an average. I notice I did the same thing over here with group 2, 2, 2, 3, and 3. I take the average and take the difference from the average, and I also get 0. I mean, they all add up to 0. So they would have the same average difference from the mean, since the sum is 0 for both of these. So the actual literal difference doesn't do me very much good. We know that the sum of the deviations from the mean, the deviations meaning how much it actually differs between the numbers and the mean, this is always going to be 0. It's a balance point, the mean is, and so these differences are always 0, which means when you add them up, you always get 0. So you can't use this as an average difference like it stands, because it just doesn't work. So here's how we come up with the formula for standard deviation. So we want something that's going to give me a typical or an average difference from the mean. So we start off with this idea of finding the differences, but instead of just taking the literal differences, we're going to square them. And the idea is that if we square those differences, what we're going to get is a positive number every time. So the negatives and positives are not just going to balance themselves out. So in this case, I took every number minus the mean, and then I squared those. And so I end up with a sum here of 9 square miles. Now this is going to be different for every data set. If I look up at the one at the top of the page, if I was to take all of these sums, 0.5, 0.5, 0.5, 0.5, and square those, and add them together, those squares are not going to equal 9. So I get this more meaningful sum, this more meaningful difference between 2 data sets when I square them. The other thing I want to do is I want to find on average how many differences there are. So I need to divide by how many. And we have this one little quirky thing we do with samples where we divide by n minus 1 instead of n. So even though there are 4 values, I'm going to divide by 3 instead of by 4. And just hang with me, because I'm going to talk about why we do that in a second. So just for right now, imagine that we're adding them up and dividing by how many there are, kind of. All right, this number is called the variance. This is the average squared distance from the mean then. And then we also, when we do this here, this is in square miles, and I'd really like to talk about the mean is in miles. So I want to talk about the average distance in miles. So I'm going to take this answer and I'm going to take the square root of it. This gives me my standard deviation. All right, so standard deviation is what you get when you find the literal deviation from the mean, the difference between your number and the average value. And you square it. You do all that for all of them. You add it together. You divide by the number of numbers there are to find the average, and then you square root it. The square root's going to undo that square that we did and get us back in the units we want to be in. So this is a typical difference from our numbers and the average. So it's kind of like saying, on average, how far away from the average are we? So I would read this as 1.73 miles is a typical amount that an observed distance from school deviates from the mean of 2.5 miles. All right, so it's on average how far off the average we are, standard deviation. So the formula that we get for this is on your formula sheet, and you'll see it says the square root of the sum of x minus x bar squared divided by n minus 1. Okay, the symbol we use for standard deviation is S when it comes from a sample. And we use this fancy letter over here, which looks like an O with a nose. That's the Greek letter S for sigma. It's a lowercase sigma. And that is when we use for the standard deviation of the population. So little s is sample standard deviation, and sigma is population standard deviation. We also have this phrase variance. Variance is the square of standard deviation. So if I say s squared or sigma squared, both of those are called variance. All right, now these are on the formula sheet, but almost always when we go to compute these, we're just going to pull them from our calculator from that one variable statistics command. So what you need to be able to do is understand a couple of things about the standard deviation formula and kind of philosophy of how standard deviation works. And then you need to be able to compute standard deviation in your calculator from a data set. All right, so things that you need to understand. So first off, why do we square those differences? If we want to find the average difference from the mean, why is that square part of the formula? And the idea there is because the sum of the differences, the deviations, is always 0. So since it's always 0, if we square them, we're going to get something that's not equal 0, and it gives us a more meaningful sum to compare to those values. The other thing is, well, what about this n minus 1? Like, why is it an n minus 1 instead of n? Because when we find an average, we divide by how many there are. So if we divide by n minus 1, that doesn't seem to work. Like, why would we do that? And so remember from previous lessons that we talked about, when you take samples, it's possible like the mean could be a little too big or a little too small, and the shape is usually pretty close, but that the range and those other spread numbers are always going to be a little too small. Your sample, it is very difficult to get all of those extreme values in your sample. If I take a sample of Avon High School students, the chance of me getting the tallest and the shortest person in my sample are very slim, which means that range, always a little too small in my sample. Standard deviation works like that too. It's always a little too small. So what I'm going to do is, since I know it's going to be a little too small, what I'm going to do is I'm going to divide by n minus 1 instead of n, because n minus 1 is a little bit smaller. And so when I divide by a number that's a little bit smaller, it gives me a value that's a little bit bigger in a fraction. And if my quotient is a little bit bigger, then my standard deviation is inflated just a little bit. And what that does is that makes my sample standard deviation calculation closer or a better estimate to what the true population standard deviation probably is. So in other words, since I know that standard deviation is going to be too small, then I go ahead and just inflate it right from the start. I'm making it just a little bit bigger in hopes that that number will be a little bit better. Okay, so why do we use the square root of the value instead of just leaving it as the squared value? Mostly that's for units. The variance is in square units, and that's not very helpful to us. It's much more meaningful to talk about it in the same units as the mean. So kind of like since we squared them at the beginning to make them positive so that the sum is not 0, we're kind of unsquaring it now. We're square rooting it to get it back to where we started. Okay, and then when do we want to use mean and standard deviation as center and spread? We want to use these when we do not have heavily skewed and we do not have extreme values. So if you see like a little bit of skew or something like that, you're probably okay to use the mean. But otherwise, you want to make sure that if you see that heavy skew or those outliers, you're going to want to use median and interquartile range, because those are resistant statistics and they're going to be much more a better representation of what is a good value. Now, if you do have those approximately symmetric distributions, though, we really like mean and standard deviation because they compute every single value of the data is included in those computations. And that's a much more appropriate way to talk about center there. So without calculating, which sample would you predict to have the smallest standard deviation? So remember, standard deviation is on average the distance from the mean. So small standard deviation means small distance from the mean. So I would look about where I think the mean is, and it looks to me like number 1 here has more values close to the center and less values to the side on average than these other ones do. So I would expect 1 to have the smallest standard deviation. Now 3 over here I think has the largest standard deviation because on average it has more values far away from the center. And then 2 is kind of in the middle. Here's another one with some histograms. And again, I look sort of at the middle of each of these. It looks to me like the smallest standard deviation here comes from this 3 because most of my values are right there, right up against the average. And the largest standard deviation would be 2 here because most of the values on average are very far from the mean itself. Now, if I was going to compute these in my calculator, I could use the one variable statistics. So let me go ahead and bring up a new document here. And I'm going to enter these values. So here's my calculator. I want a new document. I do not want to save my old document. And I'm going to do a list in spreadsheet. I'm going to go up and I'm just going to call it X. And let me find my paper that's got the values in it. This is what everybody wants to do while they're waiting on the video, is wait for me to get to my numbers, right? All right. So, all right, so here we go. So my numbers are 2 and 4 and 4 and 5 and 7 and 8 and 10 and 11 and 12 and 15 and 16. All right, so there are my 11 data values here. All right, so what I want to do, and make sure you have a variable up here. You always want that variable. I'm going to take these variable and I'm going to go, oops, I didn't mean to press control, sorry. I'm going to go menu and statistics, stat calculations, and one variable statistics. We only have one list. I'm going to select that variable X from the drop-down menu. And from this, I'm going to get all kinds of good information. So I end up with a mean X bar of 8.54. I get my sample standard deviation of 4.6554. I can get my median of 8. And to calculate interquartile range, I need Q3 minus Q1. So 12 minus 4 is 8. Okay, so I'm going to go back to my handout here really quick. So there's the mean, the standard deviation, the median. I had to compute the interquartile range. And if I had to take a guess, 8.5 and 8, those are fairly similar to each other. So I would probably guess, if I had to make a guess of shape just based on these two values, I would guess that it's approximately symmetric. Now, with that being said, remember this is kind of like squares and rectangles. If you have a distribution that's approximately symmetric, then the mean and median will be very close in value. But just because your mean and median are close in value does not necessarily mean 100% that your distribution is approximately symmetric. So you want to make sure you're interpreting this with a little bit of caution. Now, the other data set you'll notice is exactly the same, but instead of 16, I have 160 here. So the great thing about the TI Inspire now is I can actually go in and just edit that value 16 and turn it into 160, and all the rest of my data values are going to adjust accordingly in this report I already have. So here's my X bar is 21.636. There's my standard deviation, 46. I can find my median, 8, and you'll see that my 12 and 4 are still my quartiles, and so I still have the same interquartile range. If I had to take a guess, I would see that the mean is now much larger than the median. So on a number line, the mean is to the right of the median, so I would guess that this is skewed to the right. Okay, so the mean tends to follow the skew. If the mean is on the right of the median, it's probably skewed right. If the mean is on the left of the median, it's usually skewed left. Okay, so those are my values. So what would I expect to happen to the mean and standard deviation if? Okay, so remember mean is think about mean, how it's calculated. If I remove a high outlier. So for example, I've got 3 test scores and I got one really high one. If I drop that, I would expect my overall average, my typical value, to go down. Okay, but the standard deviation, if I'm dropping that extreme value, then I have a smaller spread in general, and the standard deviation is probably going to act like that as well. So the standard deviation is going to go down. If I got rid of a low outlier, so imagine like I drop your lowest quiz score, we would expect your average to go up. But remember, standard deviation is a measure of spread, and so I just made that data set have less variation, so we would expect that standard deviation to go down as well. All right, so another thing just to be prepared for is sometimes we're going to deal with mini-tab output. So in your notes, I just gave you an example of something you might see. A lot of times we'll have this more when we talk about bivariate data in Unit 2. But on here, I have this question, what's the interquartile range? And then what's your best guess of shape? So interquartile range here, I'm going to take Q3 minus Q1. Okay, I got 135. If I had to guess the shape, if I was going to take a guess, the mean is 287 and the median is 270. So since the median is smaller than the mean would be on the right. I'm going to guess skewed to the right. If I wanted to check for outliers, I would use my 1.5 interquartile range rule. If I take Q1 minus 1.5 interquartile range, I get negative 9.5. And Q3 plus 1.5 interquartile range, I get 530.5. That gives me an outlier fence of negative 9.5 to 530. If I check my minimum value, the minimum is inside the fence. If I check my maximum value, the maximum is inside the fence. So I don't have any values outside the fence, so I have no outliers. All right, now one more video sort of after this, which is the rules for means and variances, which you can see peeking out down here below, but I'm going to do that on a separate video. So remember, in general, standard deviation is an average distance away from the average. And if you are going to talk about standard deviation, for example, in sample B here, this 46.059, I would say something like 46.059 is a typical amount that an observed data value, depending on what the context is deviates from the mean of 21.636. The mean is a typical value of the variable. 21.636 is a typical value of whatever variable we collected here. Okay, so mean, a typical value of the variable, and standard deviation, a typical amount that an observed value differs from the mean. All right, thank you much.